Okay, question 6. Now, the first bit is fairly straightforward. Calculate the wavelength of the waves on the string. We know that 101.2 meters is 1.5 wavelengths. So that's a whole one there and a half. So 1.2 is 1.5 lambda. Divide 1.2 by 1.5 and you get 0.8 meters. That's 1 mark. B asks you to calculate the frequency of vibration. Well, we know that C equals F lambda. Therefore, frequency is C over lambda. 200. The velocity should be V. But anyway, C 200 divided by 0.8, and that's 250 hertz. Now, C is tricky, and I think this is probably, forget about that bit there. You want to first think about how far does the wave move. Remember that a standing wave is the superposition of two waves that are travelling in opposite directions in the string. So on this picture I've just drawn here, the black wave that we see in our book here is the superposition of the two waves moving in opposite direction. And I've drawn in a dotted red line the red wave, and it's in phase with a green wave. Okay. Now, if the distance travelled is velocity times by time, and we know the velocity is 200 meters, then 200 times by 3 milliseconds gives us 0.6 meters. So we know that each of these two waves, both the red and the green, have travelled 0.6 meters. We know also that the total length of this setup here is 1.20 meters, and that kind of gives us a clue that we're on the right track already. So if I say the green wave is going that direction and the red wave is going that direction, then all I'm going to do is I'm going to say, well, this end of my red wave green wave has now got as far as there. So I'm just going to start this whole picture for the green wave and draw it like that, and it's got as far as there. Of course, I need to basically extrapolate this back and do something like this and do a bit of that. But I fundamentally took that bit and moved it to halfway over, which is why I started there. If I take my red wave, let's say this bit over here, he's now going that way, I'm going to put that end to the middle there, so he's now going to go to there. I'm going to draw that up like that and carry it on. So that's moved that way, and of course I'm going to extrapolate it all back, and we see right away that these two waves are now out of phase. If I draw the superposition of these two waves, we find that of course it's a flat line. So what you're looking for is a flat line. The explanation of it is kind of hard to put into words to write down, but I would say the waves are moving in opposite direction. Okay, waves move in opposite direction. They've moved, I don't know, it's hard to say, really is hard to say and put it into words because they've gone in and out of phase since then as well. But opposite direction and are now out of phase. Best to do with the diagram, I think, in this situation. Anyway, that's question 6. That's why it is.